Welcome everyone to the next episode in our short series about communication protocols of embedded systems. Today we'll introduce the SPI protocol. After this short tutorial, you will be able to tell if SPI is the protocol of choice for your specific problem, understand the actual transmission flow, read and write registers over SPI, and debug faulty SPI communications. As always, we will start with some basics about SPI. SPI stands for Serial Parallel Interface and is a synchronous serial communication interface much like I2C. SPI was designed by Motorola, which is now NXP, in the early 80s and is nowadays a de facto standard as an embedded systems interconnect. Its typical usage incorporates the connection to, for example, display controllers, flash storage, or specific sensors which simply require more throughput. Similar to I2C, it follows the master and slave methodology, but in contrast to I2C, only one master is allowed here. Still, this master can connect to multiple slaves. Different configurations and modes of SPI exist, which we will introduce later on, but let's start with the typical setup. An SPI master connects to a slave using 4 wires in addition to ground. These wires are termed SCLK, MISO, MOSI, and CS. SCLK stands for serial clock and is the synchronous part of the protocol. The master which schedules all communication drives this clock line with a certain frequency. MISO stands for master input and slave output. This wire is used to transmit data from the slave device to the master device. MOSI stands for, you guessed it, master output and slave input. So this wire is used to transmit data from the master to the slave device. Sometimes MISO and MOSI are instead, for obvious political reasons, called SDI and SDO, so serial data in or out, and then need to be crosswise connected, like RX and TX for UART. But let's stick for MISO and MOSI notion for this tutorial. CS stands for chip select and is often also termed SS, so slave select. And it typically required only if the master communicates with multiple slaves. Each slave is then connected with an individual CS line to the master. If you want to connect 4 slaves, you hence need 4 CS lines. This methodology is simple, but it's also very robust. In contrast to open drain drivers and pull-ups as used in I2C, SPI uses push-pull drivers, which enhance the load capacity, the switching speed, while also minimizing the power consumption of the circuit. Thus, SPI can typically be used with much higher speeds of multiple megahertz. SPI is also very flexible in terms of the protocol itself. Generally, there are 4 different protocol modes which differ in the idle mode of the clock and in the time when data is valid. The clock polarity, short CPOL, indicates if SCLK is 1 or 0 in the idle mode. The clock phase, short CPHA, indicates if data on the MISO and MOSI lines is valid on rising or on falling clock edges. All possible combination of these settings exist, resulting in basically 4 different modes. For the ones that want to have even more flexibility, SPI can also be used in other configurations. The standard configuration which we have seen is called the full duplex mode, or 4-wire SPI. It can also be configured in a simplex or half duplex mode. In the simplex mode, only unidirectional communication, so either sending or receiving, is available. In the half-duplex mode, or sometimes also called 3-wire SPI, data is sent bidirectional over 1 wire. As the line is now shared, the master indicates reading or writing via a dedicated bit sent with the register address, similar to I2C. Okay, enough theory. Now it's time for a little hands-on experience. We will take a closer look at the following setup today. An Atmega 328P connected to an energy monitoring IC from Analog Devices, the ADE9000. This chip is soldered on this separate board here, together with some analog front-end stuff and a power supply. The wires here are the SPI lines MISO, MOSI, SCLK, CS, and ground. The Atmega on this Arduino board here is connected and powered by a computer via USB. In contrast, this energy monitoring IC is directly connected and also powered by a 230 volt mains connection. That's the thick wire going out here. Because of this mains connection, proper galvanic isolation is required so that we can never get in touch with this 230 volts on the microcontroller side here. Otherwise, we might go full electroboom if we touch it.
120 volt AC.
Galvanic isolation is handled by additional circuitry on this board here, but for us these wires will now represent a standard SPI connection. For the SPI speed, we will take a brief look into the datasheet of the IC and see under SPI timings that the fastest SPI speed possible is 20 MHz. Unfortunately, this Arduino only runs at 8 MHz, so we will be a little bit more conservative here and use just 2 MHz as a starting point. We can also see the specific communication flow that this energy monitoring IC is requiring. As always, this flow is device specific and has typically nothing to do with the specific communication protocol itself. Still, let's take a closer look at it. In order to read or write a byte, a so-called command header with 16-bit needs to be sent to the slave. We can see here that the register address we want to read or write is only of 12-bit width. After these 12 bits, a read and write bit needs to be set. The remaining bits are don't care bits. So a pretty simple flow. I've now put some demo code on this microcontroller which simply reads out the version register of the energy monitoring IC each 100 milliseconds. As always, this is fairly simple using Arduino. At first we need to initialize the SPI connection and set the corresponding SPI settings, so the speed, the clock polarity and the clock phase. So we start with 2 MHz here. The chip needs data MSB first, which we can see in this diagram here, and the clock polarity is obviously supposed to be high in the idle state. Finally, the clock phase settings need to be set so that data is captured on rising edges of SCLK. In Arduino, this translates to the defined SPI mode 3, which corresponds to CPOL and CPHA setting of 1. To now read the version register, we use 2 4-byte buffers here, one for sending and one for receiving. In the full duplex configuration, sending and receiving is done simultaneously. Hence, one call to the SPI transfer function not only sends the byte here over the MOSI line, but also returns a byte of the data received over the MISO line. We then apply to this strange data flow configuration we've seen in the datasheet, set the read bit to 1, and address our slave by pulling CS low and send each byte in the buffer over SPI. Each byte received is stored in the RX array. Afterwards, we release the slave by pulling the CS back to high. The remaining code is just for printing and waiting. So let's open the serial monitor and see if we receive something. And indeed, we receive FFFC00FE. The last 2 bytes are the data for this particular read request. Let's check if 00FE is expected here. And indeed, according to the datasheet, that's the default value of this register. Now let's hook up our oscilloscope to the bus and see what's going on there. We now set a trigger to the CS going low to start seeing something. Alright, that's actually everything there is, the complete transmission. I sketched it for you on this slide so we can take a closer look at it. As you can see, there's actually nothing special with SPI. The data is simply sent over the corresponding line, so MISO or MOSI, 1 bit at a time, and is captured according to the chosen configuration. In this case, at rising edges of SCLK. That's why data only changes here when SCLK is low. So that was reading data. Similarly, if we want to write to the chip, we simply need to set the read and write bit to write and send the 16 or 32-bit data afterwards. Perfect, we have successfully decoded the transmission. Similarly to I2C, SPI devices typically also support burst write or read of registers, so that data of the next register address is sent after the previous one. But again, this is device specific and not related to the SPI protocol itself. We can now add a little bit of code to our demo setup to read actual data of the energy monitoring IC, such as the current RMS voltage and current of the mains. If we now connect the device to the mains outlet, like this laboratory light here, we can monitor its consumption. We can also use the IDE's plot functionality to show the values over time. And with a little bit of additional tools, we can also add this to a smart home system and monitor the complete power consumption of a home. With this nifty demo, let's summarize what we've learned. SPI is a synchronous serial bus system designed to connect a processing unit, such as a microcontroller, to one or multiple other systems, such as sensors or displays. It uses a master and slave methodology with exactly one master and possibly multiple slaves. The master initiates all communications, so in order to avoid polling, we would need additional data ready lines. SPI further allows for some decent bus speeds. Even this simple energy monitoring IC here could already reach up to 2.5 megabits per second. That's it for this short SPI tutorial. If you have further questions, as always, write them down in the comment section below. If you like this tutorial, give it a brief thumbs up, and if you don't want to miss out on upcoming ones, subscribe to the channel and ring the bell.